Hello, everyone. We'll get started in just a couple minutes. All right, let's go ahead and get started. Welcome to our webinar today, everyone. My name is Justin D'Souza. I'm a quantitative specialist here at Statistics Solutions. During today's webinar, we are going to cover regression models. What is the correct regression model to run given your data? What assumptions should you check? How do you interpret them accurately? If you have any questions during the webinar, you can type those into the chat box or the question and answer box. My colleague Brittany will be assisting with questions regarding our company and how we can provide assistance. She provided some hyperlinks in the chat box. At the end of the session, I will be doing a Q&A regarding the presentation today. So if you have any questions about regression models, I will be answering those at the end. We will be sending everyone a copy of the PowerPoint and the webinar. All right, I'll start out by giving a brief overview of the services that our company Statistics Solutions provides. Then we'll dive into the topic regarding regression types, regression models, how to interpret them. I'll give a demonstration in our software, Intellectus Statistics, in which I will go through a sample regression model, how to run it, and I'll show how to interpret it as well. Then we'll conclude with a summary and the Q&A session. Our company Statistics Solutions provides assistance with every part of the dissertation journey, starting with topic development, going all the way to final defense. So no matter where you are in the process, if you hit a roadblock, let us know and we can certainly provide assistance. We have specialists that focus on quantitative studies, qualitative studies, mixed methods, literature review. If you need help framing research questions, trying to figure out what data analysis plan you should use to address those questions. We can host surveys for you on SurveyMonkey. We help with the results interpretation, both quantitative and qualitative. IRB forms, we have data entry templates that we can provide for you. And once you've completed the journey, we can help you with the journal publications. So taking your dissertation and condensing it for a journal. So if you have any questions, you can give us a call at 727-442-4290. In the chat box, there's also a schedule link in which you can speak to Janine Glace, and she will kind of break down where we provide assistance, give you time frames and price, things like that. Yeah, let us know if you have any questions. For today's topic, we're covering regressions, and it's important to first understand levels of measurement. There are three key types of variables, three levels of measurements. There's continuous variables, there's nominal variables, and ordinal variables. It's important to understand these because the type of regression model you use is highly contingent on the level of measurement of your variables. So what's a continuous variable? A continuous variable very similar, has the word continuum in it, basically, means that your variables fall on an interval or a range. So examples like test scores, temperature, weight, BMI, composite scores on a survey instrument, these are all generally considered continuous. Basically anything that's numeric that falls in a range. Nominal variables are categorical variables, things that don't have an intrinsic order. Examples like gender, ethnicity, passing or failing of an exam. You have distinct categories, but they are not necessarily ranked. When you add ranking to it, you have an ordinal variable. So an ordinal variable kind of falls under a nominal variable, under the same umbrella, but an ordinal variable is a specific type of nominal variable. Examples of this are education. You have high school, you have bachelor's degree, then master's degree, then a PhD, and then specializations. Education goes up a ladder, so this is typically considered ordinal. And a single survey question on a Likert scale, strongly agree down to strongly disagree, this is also considered an ordinal variable. So given these definitions of continuous, nominal, and ordinal, there is a specific regression type that you use for each of those measurements. A linear regression has a continuous dependent variable. So you need something numeric like height, weight, or a composite score, BMI. Those are the types of things you run a linear regression on. You need a continuous dependent, also called a criterion variable. When you have a nominal variable, something like gender, ethnicity, passing an exam, that's when you go into logistic regression. If you only have two possibilities for your outcome, like passing or failing an exam, that is a binary logistic regression. A multinomial logistic regression is used when you have more than two possibilities for your outcome. So something like ethnicity, if that was your outcome variable, then it's something like white, Asian, Black, Hispanic. You have more than two possibilities, and if that's your outcome, you do a multinomial logistic regression. An ordinal logistic regression is used when you have an ordinal criterion dependent variable. And so if you're trying to predict education level or trying to predict a Likert scale response, strongly agree to strongly disagree, that's when you use a ordinal logistic regression. Notice I haven't even mentioned the predictors. The independent variables really don't matter in terms of the selection of what regression type you use. So you can have continuous, nominal, or ordinal predictors for any of these. It's not going to impact the decision on what regression you use. The decision is based on your dependent variable. So what you're trying to predict. So just as I touched on the previous slide, the predictors can be any level of measurement. You can have continuous, nominal, and ordinal variables. As far as the coding, many times you don't want to keep variables in word format. If you have white, Black, Asian, Hispanic, you want to assign numbers to these categories. Not absolutely necessary, but it does help as you progress into the analysis. So no adjustments need to be made for continuous variables. If you have a predictor like height, weight, or BMI, you input that variable as it's originally coded. You have a dichotomous predictor, such as passing and failing. Usually you want to code the absence of a condition as your lower value. So if you're trying to predict passing rates, then you want to put 0 as fail and 1 as pass. You're trying to predict passing. So the higher value needs to be what you're predicting. And then when you get into nominal variables with 3 or more groups, this is where it can be a little more complicated. You have to follow a process called dummy coding. And there are so many YouTube videos on this. So I would would recommend checking out dummy coding in SPSS. But essentially the idea is that when you put race into a regression model, it doesn't know what white, black, Asian, Hispanic, other, it doesn't understand what those categories mean. So it's up to the researcher to assign value to those different categories. And the way we do this is by assigning a reference group. One of these 5 ethnicities needs to be the reference group, and oftentimes it's the most prevalent group. So if white is the most prevalent group in your research, you may want to make that your reference group. And what you do is you then compare the other groups to your reference. So very similar to the second bullet here, we are essentially creating 4 dichotomous variables, 4 variables with a binary outcome. We have black versus white, Asian versus white, Hispanic versus white, and other versus white. This is the key way that you interpret a nominal variable that has 3 or more groups. Then you start the actual analysis. So what you have to do first, and as you do for almost any analysis, you have to check for the assumptions. So every statistical analysis has parametric or non-parametric assumptions that you have to verify. Linear regressions are considered a parametric analysis, so they tend to have more stringent assumptions to check in comparison to logistic regression models. So you have to check things like normality, homoscedasticity, absence of multicollinearity. There are many assumptions to verify, and I can actually show you a website here. You go to statistics layered, put in, say we're doing a multiple linear regression. Statistics layered is a great reference for looking at how to run things in SPSS, but they also break down what assumptions you should check. So as you scroll down here, they have an assumption section, and you can see that for a multiple linear regression, there are 8 different assumptions. Should check. Now, depending on the reference that you read, it may say, no, you only need to check 2 or 3 of these. I think this is over-encompassing all the references I've read. There are 8 different assumptions you can check. The key ones I check are, and a lot of these are not checked mathematically. They're just definitions. Your dependent variable should be continuous if you're using a linear regression. If you're doing a multiple linear regression, you need to have at least 2 independent variables or 2 predictors. But then you get into some of the statistical mathematical assumptions. So you can check for independence of observations with a Durbin-Watson test. You can check for linearity with a scatter plot between your predictor and your dependent variable. And then you have some more like homoscedasticity and normality can be checked with scatter plots as well. It's a lot of visual interpretation of scatter plots. Multicollinearity is making sure that your predictors are not highly correlated with one another. You want them all to be independent. So there are many ways to check for that. Usually tolerance and BIF values are used. And very early on, even before you get to the regression, you should check for outliers. You want to identify if there are any extreme cases or extreme scores that you may want to take out because it could skew the findings of your regression model. So very good reference, Statistics Layered. I'll put this in the chat box. And they go into assumptions for ANOVAs and t-tests and pretty much any analysis that you'll use today. Okay, so once you run the regression model, there are 3 steps that you should follow. The first thing you want to do is you want to interpret your omnibus test. So you're going to look at, if you're doing a linear regression, you're going to look at an F-test. If you're doing a logistic regression, you're going to look at a chi-square value. And significance is usually denoted if the p-value is less than 0.05. The next step is interpreting the coefficient of determination. This is the R squared, or the McFadden's R squared, or a Nagel-Kirky R squared. There are many values you can look at that. R squared is used for linear regressions, and McFadden's R squared is used for logistic regressions. Now, step 3 is contingent on step 1 being significant. So if your omnibus test is significant, you do have a p-value less than 0.05, then you want to interpret the strength of each predictor in your model. And the way we do this is with a t-test for a linear regression and a wald test or a chi-square test for a logistic regression. And if it's significant, that's when you interpret these values and you interpret the beta coefficients and odds ratios. If it's not significant, if step 1 is not significant, you don't go to step 3. You kind of just stop right there. So let's go through a demo. And I'm using our company software, Intellectus Statistics. And this is a software that can be used to crunch numbers. So let me just select a data set here. I'm going to do, let's find linear regression right here. Okay, this is what Intellectus looks like. It's basically what Excel or SPSS looks like in terms of the spreadsheet. You have columns are your variable names and rows are the participants or the unit of interest. So in this spreadsheet, we have a series of car models, Mazda RX-4, Toyota Corolla, and we have different variables. What is the miles per gallon? How many cylinders does each car model have? What is the weight? So in this menu, you can clean the data. You can replace missing values with imputation. You can remove for outliers. You can compute variables of interest with a composite score. And you can transform data. If it doesn't follow a normal distribution, you can transform it to different formats. You don't need to do any of that data management for this one. It's already been done. But then you can go to analyses, and the first thing a results chapter typically starts with are descriptive statistics. All right, so you go to descriptives and descriptives again, and we now need to add our variables of interest. Okay, so I can just put miles per gallon, cylinders, all this stuff, illustrate, and Intellectus is going to know if you have a categorical variable, something like engine type, it's going to give you frequencies and percentages for this variable. Engine type falls into V-shaped or a straight engine. So there were 18 V-shaped engines, which represents 56.25% of the sample. Now, if you have a continuous variable, which is everything else, numeric values, weight, miles per gallon, it's going to give you the minimum value, the max, the sample size, the mean or the average, and the standard deviation. Okay, so for instance, miles per gallon, the car that had the lowest miles per gallon was 10.4, car with highest was 33.9. Average miles per gallon was 20.09. So then what you can do is you can run all these different types of analyses. We're focusing on regressions today, but as you can see, there are many of them, ANOVAs and t-tests, and correlations. We are going to go under the regression menu here, and we are running a linear regression. And what I'm going to try and predict is we want to see how does the weight of a car and how does the horsepower of a car predict the miles per gallon of the car. Okay, so miles per gallon is our dependent variable, which is a scale or continuous measurement, means the same thing. So because it's a continuous outcome, we are going to use a linear regression. So I'll go to analyses and linear regression. Our dependent variable will be miles per gallon. And our independent variable, we're going to select weight and horsepower. Okay, and at the top right here, we have the options box. Here you can see what assumptions are going to be checked. So we have normality, and we have homoscedasticity, and variance inflation factors for absence of multicollinearity. So we have 3 of the assumptions being checked here. These are the 3 I typically check. We'll save the options and click calculate. And Intellectus is going to give you a full write-up and an APA interpretation. Okay, so it first checks for normality with a QQ scatter plot. And if you hover your mouse over the figures, it gives you an explanation, and it'll tell you what the plot should look like if normality is supported and what it looks like if it's not supported. Ideally, for a QQ scatter plot, you want the data to closely follow on this diagonal line, which it does. Slight deviations, those could be some outliers that you might want to examine, but for the most part, it's following that diagonal line very closely, which means the assumption is supported. The next assumption is homoscedasticity, and this is looking for random scatter and random spread in the responses. As we can see here, we don't want to see a straight line. We don't want to see a parabola or exponential curve. We have random scatter here, demonstrating that this assumption was supported. The third assumption, multicollinearity, is making sure that weight and horsepower of the cars are not highly related to one another. And that is checked with variance inflation factors. Okay, so ideally, we want the DIFs to be below 10 right here. And if they are, that means the assumption is supported. And both these values are below 10, meaning that weight and horsepower are not highly related, which is good for the regression model. You want your predictors to be independent of one another. Okay, so that's the assumption checking. Now we get to interpretation of the regression model. So coming back to the presentation, a little bit too far here. Okay, the first thing you want to do is interpret the omnibus test first. Okay, that's looking at the f-test for a linear regression. And that's right here, okay? The first thing that is interpreted is the f-test. And it's also right here, okay? It's the note at the bottom of the table. So what this note is telling you, and you want to look at the p-value, it's telling you whether weight and horsepower together predict miles per gallon. And as we can see here, it is significant. So we do have a collective significant relationship between weight, horsepower, and miles per gallon. That's step 1. So keep that in mind that we have a significant omnibus test. That means we are going to proceed to step 3. But in between there, we have step 2, interpret the coefficient of determination, which is the r² value. And we can see right here, the r² is 0.83. We convert this to a percentage. So you move the decimal over right twice, and that would be 83%. And that value is interpreted right here. So 83% of the variance or the change in miles per gallon can be explained by weight and horsepower. Okay. And the final step is if you have a significant omnibus test, which we do in this example, then you interpret the strength of each predictor in the model. We're using a linear regression here, so we use t-test. Okay, so we look at weight, we go all the way across the row, and we look at the p-value, which is significant, and we look at horsepower, and we go all the way down, and this is also significant. So both weight and horsepower on their own are significant predictors of miles per gallon. Now, you can then interpret this beta value. This gives you the directionality and how miles per gallon changes based on a shift in weight or horsepower. So the way you interpret this one, weight, with every 1 pound increase in weight, actually, I don't think it's in pounds, might be, yeah, it's in tons, it's in tons. So with every 1 ton increase in weight, the miles per gallon on the cars decreases by about 3.88 units. So we have a negative beta value here, which means we have a decrease. Weight increases, miles per gallon decreases. Likewise with horsepower, we have a negative beta. So that means is horsepower increases by a unit, miles per gallon tends to decrease by 0.03. So these are both considered inverse related. You know, they're inversely related to miles per gallon. As these two values increase, miles per gallon decreases. That's a linear regression. We can also do a logistic regression. Now, what do you need for a logistic regression? You have to select a dependent variable that is nominal. So we have these two here. They have to be categorical, not numeric. So what we'll do is we'll try to see whether the weight of a car can predict whether the car is an automatic or manual transmission type. Okay, so does weight predict transmission type? Again, I'll go to analyses, and we're going to select a binary logistic regression. Why is it binary? Because the outcome only has two possibilities, straight or automatic and manual. Good, binary logistic regression. You first select your dependent variable. It is going to be transmission type. And you have to select a reference category, which in this case will be automatic. And then the independent variable will be weight. Okay, so when you do a logistic regression, there aren't the stringent assumptions that you have to check for a linear regression, because this is not considered a parametric analysis. So as we look at the omnibus test again, so the omnibus test for this is a chi-square test as opposed to an F test, and we do have significance. Then we interpret the R squared value down here, 0.56. So we shift the decimal over right twice. That's 56% of the sample, or 56% of the variance in transmission type can be explained by the weight of the car. And then we go inside the table and we look at weight on its own. So weight is a significant predictor. Then you look at the beta and the odds ratio. So if the odds ratio is above 1, that means you have a positive relationship between your predictor and your outcome. If it's below 1, that means you have an inverse relationship. Okay, so in this case, we have an inverse relationship between weight and transmission type, meaning that as weight increases of the car, the odds of you using a manual car decrease. So basically, the higher the weight, the more likely it is to be an automatic car. Okay, so that pretty much covers the interpretation. If you're a few steps back, like maybe in the methodology, and you're trying to figure out the research questions and how to write up your data analysis plan, we have data analysis plans here. So data analysis plan, if I go to regressions and linear regression, this is going to give you a sample research question in addition to sample hypotheses. And then it's going to go through the interpretation of a multiple linear regression and what assumptions to check. And we have references at the bottom as well. And there's also power analyses. So if you want to know what is the minimum sample size I need to target for my research, you need to run a power analysis. And it's based on the analysis that you selected. So if we're doing a linear regression, the sample size is determined on the number of predictors you have, the statistical power you are using, and the effect size. So what we provide here are 3 sample write-ups, depending on what effect size you select. And typically you go with a medium effect size if you don't have literature in your topic to say otherwise. Medium effect sizes are often used in the social sciences. It's the most conventional choice to make. Just go with a medium effect size. And it's also based on the number of predictors. Okay, so here we are only using 1 predictor variable by default, and this yields a sample size of 55. So you would need to target 55 participants, ideally, to run a regression with only 1 predictor. At the top left here, you can change the number of predictors you have. So in the example we did before, we had 2 predictors. And the more predictors you add, the higher the sample size requirement. So with 2 predictors, you need 68 participants. And just to illustrate, as we go up to 10, if you have 10 predictors, then you need 118 participants. Okay, so that's pretty much covering intellectus. We have the data management process. You can also generate plots. If you wanted to see, for instance, miles per gallon, or let's do weight with miles per gallon, and develop a scatter plot to visualize that relationship. You can edit the colors, to change it to grayscale according to APA. There are so many different plots that you can run in here. So yeah, check out the software if you have any questions. We've double-checked everything with SPSS, so the findings will match. This gives you a huge advantage because it gives you a APA interpretation. But yeah, that pretty much covers the webinar for today. So if you're trying to predict an outcome, prediction is the key word here when running any regression model. We're trying to predict a dependent variable. And then you want to determine what's the best method. And the best regression model is going to be selected based on your dependent variable. In NUS, you do a linear regression. If it's binary or dichotomous, you do a binary logistic regression. And then you have ordinal outcomes, like strongly agree, neutral, disagree. That's when you do an ordinal logistic regression. Then you want to verify that your assumptions are met, and then follow the 3 steps for interpretation. You look at the omnibus test, and you interpret the R² value. And if you have a significant omnibus test, you interpret each predictor on its own. And you can use intellectus statistics or SPSS or Stata. There are many softwares you can use to run the model. So that covers the webinar. We'll now do a Q&A session. If you have any questions, you can give us a call at 727-442-4290, or you can email us at info@statisticsolutions.com. And we'll send everyone a copy of this webinar and the PowerPoint. If you have any questions, you can type those into the chat box. Looks like we have a question from Deborah. Is there any advantage to doing an ANCOVA versus regression or ANOVA separately? I tend to only use ANOVAs and ANCOVAs when testing for differences. So if you're testing for differences in a variable between groups, differences is the key word there that usually indicates a t-test or an ANOVA should be used. If you're trying to predict an outcome, I think regression models are the way to go. So I would say probably go with a regression model if you're selecting between the two. I think it's the better option to try and predict an outcome. Okay. Yep, you're welcome. Do you have any other questions? Okay. Any other questions? I should show our company website. So if you have any questions about a particular topic, you can go to the previous webinars that we've done, our webinar archive. It's statisticsolutions.com. And here we have recordings of all the different webinars we've done, which there's a variety of topics, chapter 1 all the way to chapter 5 and defense preparation. And then you can see the upcoming webinars over here. Like we have one tomorrow on mastering the literature review. All right, any questions about regressions, power analyses, the Intellectus software? All right. Well, come join us again, everyone. Thanks for joining. We will send everybody a copy of this, and just let us know if you have any questions. If you hit a roadblock, give us a call, and we'll definitely be able to steer you in the right direction. Have a great day, everyone. Thanks for joining.